Good day. Welcome to the final video on Chapter 1.7 on cross products. Alright, let's start with a question. So given a line and a plane, what possibilities do exist for the intersection? Pause and think about this for a little while and then play again. Did you try it? Well, the answer to this question is in Theorem 1.7.22. I hope when you thought about this, you thought of a couple of possibilities. Now let's have a look at Theorem 1.7.22. Consider a plane P and a line L in 3D. Then exactly one of the following three is true. So one of them happens. L and P intersect in exactly one point. The line is completely contained in the plane, so every point of the line is a point on the plane. Or the line and the plane do not have any points in common. So every point of the line is not on the plane P. Were this the three possibilities that you thought of? Well, please do some examples to see in an example of each. Alright, now let's tackle this problem. So let n be the non-zero vector minus 2, 3, 2, and let r be the vector 2, 2, 0. So we can define a plane P to be the set of 3D vectors such that n dot x minus r is 0. And let line L be the set of 3D vectors of the form 1 plus 2t, t minus 1, 2, where t is a real number. And we want to find, does the line intersect the plane P? And if they intersect, find all those possibilities. Alright, so we know that one of the three will happen. Let's find out which one will happen. Alright, so let's start off by saying, do we have a nice form for plane P? And here, when you solve these kind of questions, it's always best to get the Cartesian form. Alright, so the Cartesian form for plane P is n dot x minus r is equal to 0. Now, we know what n is. N is the vector minus 2, 3, 2. And x is going to be the vector x, y, z. And r is going to be the vector 2, 2, 0. It's equal to 0. And so if you subtract those two vectors and if you dot it with that, you end up getting minus 2x plus 3y plus 2z evaluates to 2. Alright. Now we know line L is of the form 1 plus 2t, t minus 1 and 2. Now let's work out the intersection. So let's work out the intersection. So now we can say that x is sitting both on plane P and line L if and only if x is sitting on the plane and x is sitting on the line. And this happens if and only if minus 2x plus 3y plus 2z is equal to 2. And if it's sitting on the line, that means that vector x with components x, y, z is the form 1 plus 2t, t minus 1, 2, where t is a real number. Alright, so now let's do the maths. So minus twice, x is 1 plus 2t, y gets replaced with t minus 1, and z gets replaced with 2, that's equal to 2. So if you do the mathematics, we get minus 2 minus 4t plus 3t minus 3 plus 4 is equal to 2. So t is equal to minus 3. So unique solution. So here we have the possibility that the line and the plane intersect in a unique point. So we can say the only point on both is, so all that I do is I replace t with minus 3, so it's 1 plus minus 6, which is minus 5, minus 3 minus 1, which is minus 4, 2. So the only point that is sitting both on the line and the plane is the point minus 5, minus 4, 2. Alright, we're doing this in 3D, and here we found the intersection of the line and the plane. Alright, that was pretty easy. What made this calculation very easy is that we got the Cartesian equation of the plane. Alright, now what about the intersection of two planes? Before we can answer that, let's quickly have a look at Theorem 1.7.26. Let P and Q be two planes in R3 that intersect in at least one point, labeled A. If two planes intersect in at least one point, then there's another point sitting on both of the planes and it's different from the other point. And after you've proven that, then you can prove that if x is any point on the line that passes through A sitting on both of the planes and point B sitting on both of the planes and A and B are different, then if you take that line and x is any other point on the line, then that point is also sitting on both planes. So the proof is in the textbook. Do have a look at it. Now, after you've proven this little result, you get to prove a major result, which is the following major result. Let P and Q be planes in 3D. Then exactly one of the following is true. P and Q do not intersect, or the intersection of P and Q is a line, or that the planes are identical. So when I say that exactly one of the following is true, we are either in a scenario where this is true, false, false, or this is false, true, false, or this is in the scenario of false, false, true. So exactly one of the two happens, all right? And this is an important result because it tells you that if you have two planes and you want to work out the intersection, that you either have no point, or the intersection is a line, or the intersection is any one of the two planes because they are the same. All right? So this is one of three things that can happen when you look at the intersection of two planes. All right? Let's have a look at an example. So say you have a plane P that passes through vectors P, Q, and R. That's plane P. Let plane Q be the plane whose Cartesian equation is minus 2x plus y plus 6z is equal to 3. We want to find all points common to both P and Q, if they exist. Remember, we could have a scenario where the two planes don't have any points in common. All right. Now, when you do this, important that you want to have the Cartesian equation. So let's start with plane P. All right. So we know how to work out the normal. If we're given any 3 points, P, Q, and R, the normal is worked out as P minus R cross Q minus R. So P minus R, if you subtract those two vectors, then you get 0, minus 1, 2. Q minus R, if you subtract those two vectors, you get 1, 0, minus 1. And if you do the cross product, pause, work out the cross product and see, do you agree with 1, 2, 1? All right, and now we can see that this is not the 0 vector. So P, Q are not all on same line. So we know that there does exist a plane P that passes through these 2 points because P minus R cross Q minus R is not the 0 vector. And now we also know the normal of this plane, which is 1, 2, 1. And now we can say that the formula is n dot x minus r is equal to the 0 vector. And the normal is 1, 2, 1. So we know it's of the form 2x plus 2y. The coefficient of x should be 1. So it's x plus 2y plus z is equal to, we know that the point R is on it. And R is the vector 1, 1, 0. So we know that we're going to get x is 1, y is 1, z is 0. So that's 3. So that is the equation for plane P. X plus 2y plus z is equal to 3. So we have the Cartesian equation. So the Cartesian equation for plane Q, sometimes you've got to work it out. But here we were given it on a silver platter. It's minus 2x plus y plus 6z equal to 3. All right. So plane P, we have the Cartesian equation. Plane Q, given on a silver platter, the Cartesian equation for plane Q. All right. Now, we need to work out the intersection of these two planes. All right. So let's see, can we prove that the two planes are not the same? All right. Now, note that 3, 0, 0 is sitting on plane P. So all I've done here, in equation 1, I made y and z 0. If you solve it, you get x is 3. So we see that the point 3, 0, 0 is sitting on plane P. All right. You could use any other point. But the point 3, 0, 0 is not sitting on plane Q. All right. Because if x is 3, you get minus 6 plus 0, which ain't 3. All right. So we saw that this point is sitting on plane P, but this same point is not sitting on Q. All right. So what can we conclude? We can conclude that P and Q is not the same. So they have to be different planes. So this is good news, because this means that in our theorem that P equals Q does not happen. Alright, so it means that for the intersection is either a line or they do not intersect. They don't have any points in common. So by the process of elimination, we know that possibility 3 doesn't happen. But we still have to work out which one happens, number 1 or number 2. So for that, we try to find a point common to both. So we try to find a point common to both. Alright, so to find a point common to both, let z equal to 0 in 1 and 2. So then we get that x plus 2y is equal to 3, and we get that minus 2x plus y is equal to 3. Let's call this equation 3, and let's call that equation 4. New equations, new names. And now I'm going to take number 3 and I'm going to double it, so that becomes 2x plus 4y is equal to 6. Let's call this equation 5. You can see why I do this, because now if I add 4 and 5, I get 5y is equal to 9. And so I get that y is equal to 9 over 5. And a little bit of work, you do the maths. Do you agree with me? X is minus 3 over 5. So we see that the point when x is minus 3 over 5, when y is 9 over 5, and z is 0, is sitting on both plane P and plane Q. Alright? So we found a common point to both. Maybe you did different mathematics. Maybe you made z 10 and you found another point common to both planes. But what we can conclude here is that the two planes share at least one point. What is our conclusion? So P intersect Q is not the empty set. Alright, so let me scroll back to the big important major theorem. P and Q have, in this example, do have at least one point in common. So this is the scenario that must happen. P and Q is not the same. P and Q have at least one point in common. So that means possibility 2 happens, that the intersection is a line. So let's quote this. By Theorem 1.7.27, we can now say we have enough evidence. By Theorem 1.7.27, we see that P intersect Q is a line. Ladies and gentlemen, this is very important. We see that the intersection is a line, alright? And now we need to find another common point. So now we can do something similar. Now we can say let z equal to 1 in equations 1 and 2. And what do we end up getting? If we do this, then we get x plus 2y is equal to 2. We get minus 2x plus y is equal to minus 3. Let's call this equation 6 and 7. So I'm going to leave it for you. So double equation 6 added to equation 7. If you do this, you end up getting that y is equal to, this time around, 8 over 5. And x is equal to, y works out to be 1 over 5. Apologies. And x will work out to be 8 over 5. So let's summarize. So we get that the point 8 over 5, y is 1 over 5, z is 1, is sitting on both P and Q. So we know that the two planes intersect in a line. And on this line, we found 2 points on the line. We found this point. Let's give this point a name. Let's call it A. So let A be this point. And so let B be the point 8 over 5, 1 over 5, 1. So we know that the two planes intersect in a line. We found at least one point on the line. We found another point on the line. If your calculation is slightly different, you would find different points. All right. And now we can finally say that the answer is, let's give the vector equation for the straight line. So it's x is b plus t times a minus b, where t is a real number. And so vector b is 8 over 5, 1 over 5, 1 plus t. A over b is minus 11 over 5. The second component is 8 over 5. And the last component is 1 minus 0, which is 1, where t is a real number. So we did a lot. We showed that the two planes intersect in a line, and we even got the vector equation for that line. All right? Now, guys, this is a good question for a semester test and an exam. So make sure that first you get the Cartesian equation for both planes. Then if the intersection is a line, you need to find a point that's on the one plane that's not on the other plane. So you know that the planes are different. Then you need to find a point common to both planes. So that means the intersection cannot be the empty set. So therefore, by this big theorem of Theorem 1.7.27, we know that the intersection is a line. So you need to provide evidence why the intersection of the two planes is a line. And then we proceed to find another common point, and from the two common points, we get to write down the vector equation of the line. It's a mouthful. Do practice this. All right. So please do all of the examples in the textbook and the exercises to see situations of each happening. Let's do another one. Let the plane pass through points P, Q, and R as given, and let plane Q be the plane whose vector equation is, Cartesian equation, 2x plus 2y plus 2z equal to 7. And the question is, find all points common to both P and Q. So you tell yourself, this question, we have two planes. The job is to find all points common to both planes. So that theorem, the intersection of two planes should be ringing. Either the two planes are the same, or they intersect in a line, or they have no points in common. Either way, you need the Cartesian equations for both planes. So we have the Cartesian equation for plane Q. Let's quickly work out the Cartesian equation for plane P. Now, if you're given 3 points, P, Q, and R, you first need the normal. So the normal is P minus R cross Q minus R. So P minus R is the vector minus 1, minus 1, 2. Q minus R is the vector 0, 1, minus 1. So if you go the cross product of these two vectors, do the calculation. Do you agree that it's the vector minus 1, minus 1, minus 1, which is not the zero vector? So this is good news. So we know, because this is not the zero vector, that there is a unique plane passing through points P, Q, and R. And now we proceed. Now we work out the Cartesian equation. So it's n dot x minus r is 0. So the normal is minus 1, minus 1, minus 1. Vector x is the vector with components x, y, z. R is the vector with components 1, 1. If you simplify it, you get the Cartesian equation for plane P. It's not unique, but you get a Cartesian equation minus x minus y minus z is equal to minus 3. Now, we were given the Cartesian equation for plane Q on a silver platter. It's 2x plus 2y plus 2z equal to 7. Let's call that equation 2. All right. So now we're going to work out the intersection. All right. Now, I quickly want to mention the following, that if x is sitting on both plane P and Q, so let's rather call it if and only if. So x is sitting on both planes. If and only if x is sitting on plane P and x is sitting on plane Q. This happens if and only if vector x satisfies equation 1 and 2. So that means that if vector x is the form x, y, z, then minus x minus y minus z is equal to minus 3, and 2x plus 2y plus 2z is equal to 7. All right. Now, if you look at equation 1, the coefficients of x, y, and z is the same. If you look at equation 2, the coefficients of x, y, and z is the same. All right. So let's take equation 1 and we double it. So then we get minus 2x minus 2y minus 2z is equal to minus 6. Let's call this equation 3. We can repeat equation 2. So we get 2x plus 2y plus 2z is equal to 7. And now let's add the two equations. So if we add the two equations, we get the x's disappears, the y's disappears, and the z disappears. So we get 0 is equal to 7 minus 6, which is 1. But this is false. This is false. So no point x, no 3D vector x exists, so that x is sitting in P intersect Q. Hence, the intersection is the empty set. So, as a remark, so if P intersect Q is the empty set, then you can always get a contradiction. If you look at the Cartesian equations, get a contradiction if you look at the Cartesian equations of both planes. Alright, so the only example that we didn't do in this video is that if you have two planes and that are identical, so the intersection of the two planes is either one of the planes, but for that, have a look in your textbook or some of the exercises. I hope you enjoyed this video. Next time we will be doing a video on chapter 1.8. Have a good day. Bye.